Hi, today's lesson's on complex numbers and their operations. So for our first example, we're going to show where this comes from. Where do complex numbers come from? And it basically happens because of square roots. So when we talk about x squared equals 16, there are two possible answers. You can just kind of guess, which is 4 or negative 4. Because if you go 4 times 4, you get 16. If you go negative 4 times negative 4, you get 16. The way we can do that easily is we just square root and just understand anytime you square root a square, you get two answers. So you get x equals plus or minus 4 if you want to shorthand it. So something happens here though. If we try to say what squared equals a negative, that's impossible. Because if you plug in a positive, you get a positive. If you plug in a negative, you get a positive. So what's going on here is we got to a problem. And this problem is we cannot square root a negative. So these mathematicians back in the day said it was impossible. But one creative mathematician, I forget his name, came up with a cool idea. He said, well, why don't I just keep solving? And what happens is he gets these things called imaginary numbers. So the way we do this is like normal. Square root of 9 is 3, but because it is negative, we just put an I next to it. So that brings us into complex numbers. Now, my best explanation for what complex numbers is they're rotational numbers. And I'll show you what I mean in a minute. But key things to note is I squared equals negative 1, and I equals the square root of negative 1. These are going to be the two things that we're going to use the most. Also, all complex numbers are written with the whole number plus the imaginary part after, plus or minus the imaginary part after. So let me give you a quick explanation of what an imaginary number is. So basically, like I said, it is a rotational number. So imagine we have a number line. We have 0 right here. We have 1, and we have negative 1. So how do we get from negative 1 right here to, or positive 1, excuse me, to negative 1? Basically, we have a couple options. One, I could just walk 2 spaces. That's called a translation. I could reflect. In other words, I can fold this paper over and make it where it lines up. So I fold this over to this side. That's like multiplying by a negative. So moving is adding and subtracting. Reflecting is multiplying. So last thing we got is rotating. So how can I get here? Well, I just rotate out of it to here, and then I rotate back in. This distance right here does not exist. So that's why we call it I. And if we rotate again, down here, we get negative I. Then we rotate back in. And so that's what imaginary is. You rotate out of your dimension, and you rotate back in. And so it is used in modern day computing, especially with 3D computing and simulation. They're called quaternions if you want to look it up. It's really, really interesting stuff. It was created by, I believe, a Scottish man, I believe. So, all right. So, but these are just numbers in general. So we can add, subtract, multiply, and divide them. No big deal. So the way we do is we add the real parts and combine the imaginary parts. That's it. So for example, on this one, what I'm going to do is I'm going to take 4 and add it to negative 4, not the 3. So if we go 4 plus negative 4, we get 0. Now I'm going to add the imaginary part to the imaginary part. So add normal, negative 3 plus 3 would be 0i. Now since this is all 0, the whole answer is just 0. Now with subtraction, I always recommend that you distribute the negative before you combine. So I have 5 minus 3i, distribute that negative, so plus 2 minus 4i, and then we just combine like terms. So 5 plus 2 is 7, negative 3i plus negative 4i is negative 7i. And that is your answer. And you must write it in real then imaginary last. Go ahead and try this problem. Try this problem. Now, multiplying complex numbers is a little bit tricky. There is one key thing you always have to remember, which is I squared equals -1. So let me show you an example. It's actually a lot easier than it seems. So if we distribute this, I'm going to get, so I'm going to take this, distribute to this one, so I get -15i. And then this one to this one would be plus 6, I times I is I squared. Now the trick with the I squared, there is a shortcut, is I could replace with -1, but if you multiply anything by -1, it's the opposite. So this right here actually becomes -6. You just change it over. And now we got to write in the correct form. So real number first, which is -6 minus 15i. So part B, same thing, we're going to do distribution upon distribution, kind of like FOIL. So we go 4 times -1, which is -4. 4 times -2i, which is -8i. We go 3i times -1, which is -3i. 3i times -2i is -6i squared. And once again, because this is negative and it has an I squared, we make it +6. And so from here, we're going to combine the real terms. So -4 plus 6 is 2. -8 plus -3 is -11i. There's our answer. So this one's kind of an interesting. If you notice, they're like the same, but there's one difference, which is the I has an opposite sign. Let's see if something special happens there. So -6 times -6 is 36. And then -6 times -i is plus 6i. And then we go backwards. I times that is -6i. I times that, it'd be -i squared. Now, once again, it's I squared, but since it's -i squared, this is just +1. And so these cancel. So we have 36 plus 1, which is 37. These right here are called conjugates. And what happens is your answer will never have an imaginary number in it. That's basically it. Go ahead and try this question. Complex conjugates. Basically, they're the opposites of the middle. So if I have, let me give you an example. If I have 2 plus 3i, its conjugate would be 2 minus 3i. You do the opposite of the i's. So with this, we get a cool pattern, which I'll show on the side right here. So let me do a general. So if I have a plus bi, its conjugate would be a minus bi. If I distribute this and multiply it normal, basically what you end up with is a squared plus b squared. In other words, if you square this first number and square the second number and add them, you have the answer. So this one, for example, we'd go 2 squared plus 3 squared, which ends up being 4 plus 9, which is 13. And so we can use that to make things a lot faster because we just did addition, we did subtraction, we did multiplication. Now we're going to do division. Division is tricky, to say the least. So we're always going to do, we cannot have I in the bottom, is basically what's happening. So the way we do this is I'm going to rewrite it using parentheses. And now we're going to multiply top and bottom by the conjugate of the bottom. Since there is an I, if there was no I, we'd be done. But since there's an I, we're going to do the conjugate of that, which is -3i. You could think of it as like 0 plus 3i and 0 minus 3i. It's the same thing. Now we're going to go ahead and distribute this. So I get -27i minus 36i squared. I just distributed the top. And now the bottom, we just get, I'm going to go ahead and show it, but -9i squared. And now anywhere there's an I squared, we're going to change the sign. So 36. This is +9. So I'm going to rewrite it in the correct order. So 36 minus 27i over 9. Now, we're not done yet because these can actually reduce. So I'm going to go ahead and separate that as 36 over 9 minus 27 over 9i. So we get 4 minus 3i, and that is our answer. Another trick, by the way, you could reduce by 3 at the very beginning if you want to. So here's one that's more common. So we go 2 plus 3i over 1 minus 4i. Make sure when you copy a problem, you copy it correctly. And then multiply by the conjugate, which would be 1 plus 4i. 1 plus 4i. Now we distribute this like normal. So I'm going to start moving quicker. So 2 plus 8i plus 3i plus 12i squared over, and we're going to use the trick I just showed you. So we go 1 squared plus 4 squared. Now, since this is I squared, it's negative 12. So I get negative 10 plus 11i over 17. And that's it, because it does not reduce. 17's prime. Go ahead and try this problem. Try this problem.